morning to all of you. I am Dr. Gaurav Saxena. I am Associate Professor in EC Department. Today I have discussed some topic regarding the magnetostatic field. So, which is useful for EN student, particularly the third semester. So, just I want to, what are the introduction regarding this? So, first one is what is the static electric field characterization in electric field or electric field density D. We have to be discussed in previous slides, and in this chapter we have to be find out the what is the magnetic field intensity and magnetic flux density, what is the relation between them by using the B is equal to mu h, and how we find the magnetic field intensity by using the law of, that means the what is the meaning of Biot-Savart law we have to be used here. So in this chapter we have to noted out the what is the static and the stationary charge which have to be used in the produces a static electric field, and if the charge is moving, so of how much force is to be corrected in the electric field as well as the magnetic field. And the static magnetic field are also produced by stationary permanent magnets. So this is the basics conditions or basics or laws you have to be just given in that particular slide. What is the basic laws? That means what is the force, Coulomb force we have to be find in the electric field, which one is the Q1 Q2 upon 4 pi epsilon naught square, and in the direction of AR. And but in the magnetic field we have to be just given the dB, where the B is the magnetic flux density, and which one is according to the that particular system magnetic system, which one is equal to the mu naught I dl cross AR upon 4 pi r square, where r is the distance between the conductor, filament conductor to the point P, where the magnetic flux density is to be defined, and the d dot ds is equal to q enclosed. This is the Gauss law, and in the magnetic field H dot dl is equal to I enclosed, so we can say Maxwell fourth equation or Ampere circular law. So force laws for the source element, which one is equal to QE and the QU cross P in the magnetic field. So in the field intensity, electric field intensity, which has to be defined, electric field is equal to voltage upon length. But in the case of magnetic field intensity is defined the I upon L, where the I is the current and L is the length. Then a flux density is defined the psi upon S, and magnetic flux density is defined the psi upon S in both Weber per meter square in the case of magnetic field. In the case of the electric field, which one is equal to Coulomb per meter square. So this is the example which I have to be enclosed here, and this is the Poisson's equation del cross V is equal to minus rho V upon epsilon. You have to just see that here, and this one is del square A, which is equal to minus mu j, where A is the magnetic vector potential. So magnetic vector potential is defined by A, so we can say this is del square A is equal to minus mu into J. J is the current density. So first very important question regarding this unit, which one is Biot-Savart law. So what is the meaning of Biot-Savart law? If a current carrying conductor is to be defined here, and having if current flow is I, and if I take in this filamentary unit di dl having this length dl, and the current is flowing in that particular conductor is I, so we can say the filamentary length, which one is I into dl, and if we find the magnetic field intensity at a point P, so if this is the length joining from this conductor to the point P, this one is defined by vector R, and the angle between them is shown as alpha. So DH, which one is DH is defined the DH. What is the DH? DH is the differential magnetic field intensity, which is dependent upon the filamentary conductor IDL and the angle between them, that means the sine alpha of that particular system, or we can say IDL cross AR12, where AR12 cap, which one is defined, AR12 cap, that means the AR12 So that means the direction of that particular vector in the direction of P. So if we this cross product is, if we open, so the magnitude of IDL, which is defined here, and this is unit vector, so we can say the magnitude of this unit vector is should be 1, and the angle between them, which is denoted by alpha, so we have to be calculated by IDL sine alpha. And this magnetic field intensity also depend upon the distance between the 2 points of that is in this particular system we have to define here R12. So it decreases R12 square. That means if the distance, if we find the distance, if we increase the distance from that particular filamentary conductor, so the magnetic field intensity to be decreases by 1 by R square. So this proportionality sign is to be here, where so K is the proportionality sign. The value of this is K is equal to 1 upon 4 pi. So this DH, magnetic field intensity, which is equal to the IDL sine alpha upon 4 pi R square in the direction of AR12. So the magnitude of that particular magnetic field intensity is to be calculated by this formula, and the direction of that particular magnetic field intensity is going to in the direction of AR12. So what is this is AR. So we can say if we open this AR, that means that what is the meaning of AR? AR is the unit vector, and unit vector is defined by R12 vector upon R ka mod. So if we put here R vector upon R ka mod, so here R square and R is here. So we can say the total differential magnetic field intensity defined IDL cross R upon 4 pi R cube. So that means R is here because this AR, this unit vector AR is defined R12 upon R12 ka mod. That means this R12 is defined here, that is the direction of that particular system, and this mod is to be calculated here. And if we taking it, this one is R and this one is R vector. So this R and R square, which one is R cube, and IDL cross this one is R vector. So here, so direction of DH, so that means that this is defined what is the meaning of this and how we calculate. This is the formula for finding the differential current element here, and the direction of that particular system, which has to be determined by the right-handed screw rule, or we can say right-handed rule. So if this is current filamentary conductor, this having a length of dl, or we can say dl, if we integrate this, so the total length is L, and the current is flowing in that particular filamentary conductor is I. So that means the direction of this thumb, that means this propose which direction your current is to be flowing. So this thumb is flowing the direction of that particular current, and the differential magnetic field intensity is to be defined by that particular system here, or we can say this is counterclockwise. That means the direction of DH, which has to be defined here by using that right hand thumb rule, or we can say the differential magnetic field intensity here, which one is used by the right hand screw rule, or we can say this defined by the DH, or we can say if we put that is the one way, we have to find the which direction your differential magnetic field intensity is to be produced. But this is the another case, we have to be here. If I put it, that is the screw, what is the meaning of right hand screw rule? We have to be find the what is the differential, what is the direction of differential magnetic field intensity. So if the current is flowing here in this direction, so we can say this screw is to be tight in that particular system, this screw is moving here. Or we can say if the direction of current is flowing here, that means this screw is to be released. So we can say the direction of that particular DS should be the clockwise direction. But in the case, if the current is flowing in that particular direction, though, so the differential magnetic field intensity is to be moving down the anti-clockwise direction. So by using the this Biot-Savart law, we have to be find out what is the direction of the differential magnetic field intensity, as well as the what is the magnitude we have to be find by that particular formula. So this is very important. So this Biot-Savart law, this is the how we can say this is the current element conductor I. So we can say this is the direction of dH, or we can say this is the direction of magnetic field intensity in the direction of counterclockwise direction, or we can say here. So this is the cross-sectional diagram. This is the top view. So that means how we energize, or how we can say the what is the meaning of this. If the current is flowing in that particular direction, or we can say here, so this is the pattern of magnetic field intensity. Or we can say we have to be just, this is the right hand thumb rule, or we can say this is the this is also a right hand thumb rule, or we can say if H or I is out, so we use the dot. If H or I is in, that means the in that particular system, so we can say this is cross. So represent dot and cross, that means the if magnetic field intensity is on the paper, that means the away, so we can say dot, and the in, that means the cross. So this Biot-Savart law is to be for differential current element. This is to be characterized by three current element, that means the line current element, surface current element, and the volume current element. So if that means if the charge is distributed along the line, so that means the current is flowing in that particular length. So that means the current or charge is distributed in the line direction. So we can say this magnetic field intensity H is to be defined by IDL cross AR upon 4 pi R square. So that means this is previous one. So we can say if your charge density is to be placed and the surface current density, so if the surface current density K into ds in a particular area, so this magnetic field intensity is to be changed from line current element to the surface current element, which one is equal to the K ds cross AR upon 4 pi R square. So if your current is to be distributed in the surface type or surface direction, or we can say your current elements is to be distributed in the current surface per unit area, so that means your magnetic field intensity formula is to be converted into the IDL to the KDS. Only we change that, where K is the surface current density, or we can say di by ds. So if we multiply K into ds, so that means the di by ds into ds, that means the di. So particularly if your charge is distributed along the surface, so we can say, so we use the K element, K, that means the surface current element. And if your charge is distributed along the volume, so this formula is to be converted into the volume integral J dot dV cross AR upon 4 pi R square, where J is the volume current density, that means the J into dV. Or we can say where J is the di by dV, so that means the per unit volume, what is the current is flowing in that particular area, or we can say in a particular volume, or we can say in a unit volume. So how much current is flowing in that particular direction, so we can say this is J, and J is defined by the di by dV. Or we can say, if we put it J into dV, that means that this represents the how much current flow in that particular volume. So I into AR upon 4 pi R square, where this is the formula for in the terms of volume current density. This is the formula for surface current density. This is the formula for finding the finding the magnetic field intensity in terms of the line current density. So one question we have to be defined here. So this is the magnetic field of a straight conductor. That means that if I can say this is the diagram of, if the this is a current carrying conductor having a flow of current I. This is the differential length dl. So we find the magnetic field intensity at a point P. So the direction of P is inside that particular system, and this is the distance from O to P is rho, and the angle between these points is alpha 1, and this point is alpha, and this point is alpha 2. So what is the magnetic field intensity in that particular system? So this is the consideration, the continuation of dH and P. So because the charge is located at the 0, 0, z direction. So we can say if the charge is distributed or current carrying conductor is to be distributed on the z direction, so the differential magnetic field intensity is defined by the Biot-Savart law, or we can say Biot-Savart law. We already, this derivation we have already, or in the previous slide we have to be already discussed in previous slide. Then dH is equal to I dl cross AR upon 4 pi r cube. But if your current conductor is to be distributed as a line integral, so this dl is equal to, in the direction of, we can say this is z direction, so dl is equal to dz az. That means your line is to be distributed in the z direction, and the r is defined here is the, where the r is defined is the rho into a rho, and so dl cross ar. So what is the meaning of dl cross ar? Dl is dz into az, or r is rho into a rho, so that means the az cross a rho. So what is the, which one is equal to a rho a phi az. So this is in the cyclic order. So a rho cross a phi is equal to az, a phi is equal to cross az is equal to a rho. So in this direction, in this particular dl, which is defined in the az direction, so dl in az direction, and r, vector r is defined in the arrow direction. That means the r is defined in the arrow direction. So that means the cross product between them, which is in the direction of a phi. So dl cross r is equal to rho dz in the direction of a phi. So we have to be put here, what is the h? H is defined here. We have to be put dl cross ar. Dl cross ar is equal to rho dz. So rho dz in the direction of a phi, and I, and 4 pi. What is the r cube? R cube is the r. What is r? So this is distance is rho. This is 90 degree. So what is the meaning of, sorry, this r? So r is equal to the under root rho square plus h square. So this one is h, or we can say this distance is h. So this r is equal to under root rho square plus h square. So we put this value to there. So that means you put the value of r in under root r is rho square plus h square, which one is equal to rho square plus h square raised to power 1 by 2. 1 by 2. So we put here, this is r cube, so the power is 3 by 2. So that means this is the rho square plus z square. Because h is denoted as the 0, 0, z, we can say 0, 0, h is defined where h is equal to z. So we put h is equal to z. That means that in the direction of az direction. So the total magnetic field intensity is defined by the I rho dz 4 pi under root, or we can say rho square plus z square raised to power 3 by 2. And we solve this integral by using the substitution method. So we put the z is equal to rho cot alpha, and the dz which has to be taken by that particular formula, which one is there. So we solve this integration. We find the magnetic field H is defined in the particular system, which one is equal to I upon 4 pi rho cos alpha 2 minus cos alpha 1 in the direction of A phi. So where tan alpha is equal to rho by z and z is equal to rho cot alpha. So this magnetic field intensity in terms of I, rho and alpha 1 and alpha 2 is defined here. So that means H is equal to I upon 4 pi rho cos alpha 2 minus cos alpha 1 in the direction of A phi. So this is the basic formula or mother equation to find the magnetic field intensity, where your charge or line charge is to be distributed on the z-axis and making a angle from two filamentary conductor points having an angle of alpha 1 and alpha 2, where rho is the radius of that particular system, or we can say the distance between from here to here. So two possibilities to find the magnetic field intensity of a filamentary conductor which is associated in the z direction. That means when the conductor is semi-infinite. So that means the semi-infinite, what is the meaning of semi-infinite? So we start a conductor from 0 to, so we start a conductor from 0 to infinity. So that means 0 to infinity. So we can say this is semi-infinite length. So semi-infinite length where we put here, so that means in this condition, this is origin 0 and this conductor is to be expand in the infinity direction. So that means this alpha 2 is belong to the, in that, because this direction, this length is to be very small with comparison to the this infinity distance. So we can say this alpha 2 should be in that particular phase. So we can say alpha 2 should be the 0 degree. So because of the this length, rho length is to be very minimum with respect to the infinity. So we can say point P and point B are in same phase. So we can say this alpha 2 is to be extended. That means that this alpha 2 is to be extended, or we can say this is seen as just like this. So that means the alpha 2 and P, point P are in the same phase. So we can say this alpha 2 should be the 0 degree. But in the case of alpha 1 is here. So this alpha 1 is to be put in this, and that point, this point A is to be shifted to the A point. So we can say making an angle of 90 degree. So we put alpha 1 is to the 90 degree. So in this case, when the conductor is semi-infinite, so the alpha 2 should be 0 and alpha 1 is to be 90 degree. If we put this alpha 1 and alpha 2 in that particular mother equation of that particular system, so we put his alpha 2, cos alpha 2 is 0. So that means cos 0 is 1. This value is 1, and cos alpha 1, this cos 90 is to be 0. So the value of this magnetic field intensity for a semi-infinite length conductor having a current of I, so we find the magnetic field intensity at a point P, which one is equal to the H is equal to I upon 4 pi rho in the direction of A phi. So this is a very important formula to find the magnetic field intensity of a semi-infinite current carrying conductor. So the value of H is defined by the I upon 4 pi rho in the direction of A phi. So in the second case, so this is the first case we have to be defined here. In the second case, we have to be defined. What is the second case? In the second case, when the conductor is infinite length, point S, that means the first case is the semi-infinite. So what is the meaning of semi-infinite? So we take in a current carrying conductor from origin to infinity. So if we taking a infinite length conductor, that means the total length is defined here, the minus infinity to the plus infinity. So you remember that what is the meaning of semi-infinite? Semi-infinite, that means the one side is infinite and one side is start at the origin. And in the infinite case, if your conductor is infinite length, that means your length is to be defined in the minus infinity to plus infinity. In this case, the alpha 1 is 180 degree and alpha 2 should be the 0 degree. So what is the meaning of this? You just see that if we put here this length is to be minus infinity distance and this to be plus infinity distance, so we can say this point is to be here and this point is to be here. So we can say having a angle of this one is 0 degree and in that particular direction this one is 0 degree, but in the opposite direction we can say, because this distance is to be very small with comparison to the infinity, minus infinity, so we can say this point is to be appear here. So we can say this is the minus 180 degree, or we can say 180 degree, this one is 0 degree, this one is 0 degree, or we can say this one is 180 degree. So alpha 1, this is alpha 1, so this alpha 1 is to be here and this alpha 1 is to be here. That means this alpha 1 is to be here. So the value of alpha 1 is minus 180 degree and alpha 2 is 0 degree. So if we put here, that means what is the meaning of this? Alpha 1 180 degree and alpha 2 is 0 degree. So cos 0 1, cos 180 minus 1. So this one is 2, or we can say the value of this 2. So current so the current intensity, that means the magnetic field intensity I is equal to I upon 2 pi rho cos alpha 2. Alpha 2 is 0 degree minus cos 180 degree. So that means cos 0 1 and cos 0 1 and minus 1, that means the plus 1. So what is the value of H? H is 2I upon 4 pi rho in the direction of A phi. That means I upon 2 pi rho, because 2 2 is 4. So that means I upon 2 pi rho in the direction of A phi. So we easily calculate if your current carrying conductor is the infinite length. So the value of magnetic field intensity H, which one is equal to the I upon 2 pi rho in the direction of A phi. So this is the formula for that particular system. So this is the example 1 we have to be taken from the standard book, William Haight. So the conducting triangular loop in the figure carries a current of 10 ampere. So find the magnetic field intensity H at 0, 0, 5 due to the side of one of the loop. So what is the meaning of that? So this figure is to be given. So we put, so what is the distance of that particular system here? So this is 0. This is the origin. This distance is 2. This distance is 5. That means this is rho is equal to 5. Or this one is 90 degree, or we can say alpha, in given that alpha 1 is equal to 90 degree and this is alpha 2. So this one is, what is the value of this? This one is under root 2 square plus 5 square, which one is under root 29, 25 plus 4, under root 29. So what is the value of cos alpha 2? So cos alpha 2 is equal to base upon hypotenuse. This one is equal to 2 upon this distance is 2. This is under root 29. So 2 upon under root 29. So alpha 1 is 90. So we cos alpha 1 is equal to cos 90. That means is equal to 0. So you put it. This is semi-infinite length. So we can say we have to be put here I upon 4 pi rho. So that means we also calculated, that means the H is equal to I upon 4 pi rho cos alpha 2 minus cos alpha 1. Alpha 2 is defined. Alpha 2 is, cos alpha 2 is 2 upon under root 29 and cos alpha 1 is equal to 0. So we have to be put here cos alpha 2. Cos alpha 2 is 2 upon under root 29. Rho is equal to 5 and cos 90 is 0. So you have to put here I. What is the value of I? I is 10 ampere. So that means we have to put I is equal to 10 ampere, 4 pi, rho is equal to 5. Rho is equal to, this distance is 5. So we can say this is rho is equal to 5, which is defined here. So, and we also calculate cos alpha 2. What is the cos alpha 2? Cos alpha 2 is defined by 2 upon under root 29. So we put it 2 upon under root 29 here, and the alpha 1 is given that 90 degree. So what is the value of cos 90? Which one is 0 in the direction of minus ay? Because this one is in the case of arrow a phi az. So this is minus ay direction. So we can say what is the value of h1? H1 is equal to, we have to solve here, minus 59.1 ay milliampere per meter. Milliampere per meter. So we easily calculate what is the magnetic field intensity in that particular system, because a phi is defined because h is defined here. So that means the ax is defined in the direction of current is defined is I direction, or dl defined. That means the dl defined in the I cross dl. So the a in the direction of az. So ax cross az, which is equal to minus ay. So we can say the direction of magnetic field intensity in the direction of minus ay, and the magnitude we have to be defined by I upon 4 pi rho cos alpha 2 minus cos alpha 1. So direction magnitude is defined here, which is equal to 59.1, and the direction is minus ay, because I is defined in that particular direction, x direction, dl is defined in the dash direction. So I cross ax cross az, which is equal to minus ka ay. That means the magnetic field intensity is defined in the minus ay direction. So this is the feature of this particular video lecture. So in this particular lecture, we have to define how we calculate the magnetic field intensity, and one numerical we have to be calculated, how we find the magnetic field intensity of a current carrying conductor having in the direction of x, and the length of that particular direction in the direction of az. So we define how we calculate the magnetic field intensity by using the Biot-Savart law. We have to be taking the what is the derivation of that. If we find the magnetic field intensity of a semi-infinite current carrying conductor and the infinite length of current carrying conductor, this is how we solve this question, and what are the parameters we have to be discussed here, and what is the meaning of this, and what is the different current distribution, and we find the Biot-Savart law in different current distribution system, yani line current distribution system, surface current distribution system, volume current distribution system, how we calculate the direction of magnetic field intensity by using the right hand thumb rule or screw rule, we have to be find here. And this is the Biot-Savart law. What is the definition of Biot-Savart law? We have to be discussed, and what is the parameter of dependence of magnetic field intensity of that particular system. This is the some electrostatic equations, and so we end this today's lecture. Thank you very much.